say f is going to go from the positive nths to the positive nths. And I had a rule that says I'm going to take every positive int and map it to the odds. I could say that, well, then f of, say, n is going to go to, say, 2n minus 1. That's one way of writing it. On the other hand, I could write it as a picture. 1, 2, 3, 4, ellipsis. 1, 2, 3, 4, 5, 6, 7, ellipsis. So this is my A, which happens to be what? That's the positive nths. This is my B, which happens to be the positive nths. Where does 1 go? 1. Where does 2 go? Where does 3 go? Where does 4 go? Now, does ellipsis work? Do you see the pattern? Yes. I also could write it, I could have written it like this. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7. Where does 1 go? 1. Where does 2 go? 3. Where does 3 go? 5. Where does 4 go? 7. If I wanted to, I could write it as a set of ordered pairs. I could have said that f was equal to 1 gets mapped to 1, 2 gets mapped to 3, 3 gets mapped to 5, ellipsis. These are all functions. Right? They're all the same function. Right? Normally when I write them as ordered pairs, whether it's a dot form like this Cartesian graph or these list of ordered pairs, normally we call these two graphs. A graph of a function is the ordered pairs. This one right here with the arrows going across, that is not a graph, it's just an arrow diagram, but it's also a visualization, right? On the other hand, this is normally what like a lot of people want to go to because you've always been in college algebra. But if I went and said, please give me a function from the reals to the positive integers, and I ask for certain properties, what do I expect you to do? Something. Draw a picture. Give me a graph. Right? Give me a set of ordered pairs. Give me an arrow diagram. Give me an algebraic function. Don't care. If I tell you the domain and the codomain, you should be able to make up something just, off the top of your head with certain restrictions. Right? These are all representations of the same idea. Does every one of these represent a function? For example, let's look at this part right here. It's the same function. I've been calling it a function. I think this pays attention to when I accidentally swipe my hand on it. Did I pick the wrong day again? There we go. For every one of these, what is the two restrictions to guarantee that this has to be a function? What has to happen? Everybody on the left has to go somewhere. And when it goes, how many places is it allowed to go to? 1. So if I had this happen, what would it automatically be? Not a function. Is it still a binary relation? Yeah, I have 2 sets. Right? But it's not a function. What if all of a sudden 2 didn't go anywhere? Right? If I sit there and said, no, 2 didn't go anywhere, now would it be a function? No. Function means everybody has to go, and when you go, you only get one place to go to. What if everybody went to the number 1? That's fine. Right? It's the domain that your restriction is. All right, so that's functions. Some features here for domains. To be a function is all elements of domain must map, right? To be a function. But all of a sudden, what if I took this and I wrote that y was equal to the square root of x, and I had that graph? Is that a function? Normally in college algebra, how did you determine if a graph was a function? It had to pass the what test? Does that pass the vertical line test? But my problem would be this. What if I said that the function was supposed to go from the reals to the reals? Is it a function? No. Why not? Where's negative 1 go? Nowhere. Where's negative 2 go? Nowhere. What's a function say? Everybody in the domain has to go somewhere. But all of a sudden we've been told forever that this is a function. It's a function only in the set that, yeah, I know you asked for the reals. It's not a function if I have to include the left-hand side. So what I'll do is I'll restrict my domain to all the x's greater than or equal to 0. If that's true, it's a function. But then you ask, but you didn't tell me that. It's like, well, isn't that a natural domain? And so if there's natural restrictions, these sorts of things are called natural domains. Sure, you told me all reals. I don't believe that you meant all reals. I thought you meant what naturally makes sense, which is only the non-negatives. Because I can't take the square root of a negative number unless you want me to talk about complex numbers, and that's completely different. So what we'll do is restrict it. If you have natural domains, these are no longer called functions. They're what are called partial functions. Partial functions, f going from a to b, is the idea that the domain a has some restrictions on use. We don't use all of a. We only use, like, is there a natural restriction? What are the restrictions? There could be a natural restriction. I only want to deal with the non-negatives. We do that, so for examples, f of x is equal to 1 over x squared minus 4. We call this a function, but really, what two numbers are bad? Negative 2 and 2. So what we say is, hey, look, this is a partial function because we need to not use x equal to 2, x equal to negative 2. Those give me problems. That doesn't map anywhere, right? Because I can't divide by 0. F of x is equal to the square root of x plus 2. This is also a partial function. Because what's bad? The square root of this, the inside, must be non-negative, right? The inside has to be non-negative. Well, if x plus 2 needs to be non-negative, what are the only x's that I'm going to allow? Right? It needs to be strictly greater than or equal to 0. Move the 2 across. X must be greater than or equal to negative 2. If I plugged in a negative 3, it's not real. So we only deal with reals, so there's a natural restriction. So partial functions will be important. This will come back at the very last thing that we talk about in Discrete 2 at the end of the spring semester, because we'll deal with partial functions on Turing machines.